Okay, good morning everyone. Let's get started. So I posted the grades for exam 2 on Blackboard. I guess you've seen that. I also posted a link to a YouTube video about diabetes mellitus. I encourage you to look at that. It provides a good overview over diabetes, but also puts in context a lot of the topics that we have discussed so far. So I think it's worthwhile, and it only takes 17 minutes long, something like that. So we're going to start at least talking about lipid biosynthesis today, and towards the end of this lecture period I will talk about the exam. Okay. Are there any questions? Good. So we're still talking about anabolism. We already covered carbohydrate biosynthesis. So we're moving on to the next class of molecules we're going to discuss, and these are lipids. Remember, I gave you an overview of lipid function, structures, and things like this before we talked about the degradation of lipids, and I may have shown you this slide previously that summarizes the major functions of lipids, and typically what comes to mind first is the storage of energy. And we know that energy from lipids is stored in the form of triacylglycerols. We looked at the structure. We'll take a quick look at how these compounds are being synthesized, but our focus will be primarily on the synthesis of fatty acids, which are components, the starting components of most of these compounds. Then, obviously, lipids are of extreme importance for biological membranes. There are several hormones that are lipids. I talked about eicosanoid functions previously in my overview. We are not going to talk about the synthesis of eicosanoids really in detail here. Lipids can also be intracellular messengers. We talked about the function of bile salts as natural detergents to emulsify actually dietary lipids that you take up with your food. Vitamin K and other cofactors can be lipids. Lipids are also important as anchors to anchor other biomolecules, proteins, for example, in a hydrophobic environment like a biological membrane or so. We talked about dolicol as a transporter in the formation of oligosaccharides that are then attached to glycoproteins, and then a number of pigments are also lipids. So, if we first just take a look at this storage of energy, you should realize that lipids are extremely well suited as energy storage molecules. And to illustrate this, let's take a look at this table, which shows you a summary of the available fuels in two men with different body mass indices. Okay, so one man weighs 70 kilograms, so that's something like 100, what would that be, 150, 160 or so pounds. And then we have obese man that weighs 140 kilograms, so twice that much. This one here is referred to as a normal man, but this really refers to the body mass index, not his mental state, I suppose. And this one, based on the body mass index, is called obese. There are different classifications that you may be aware of, overweight and obese and things like this. If we compare the different types of fuels they have available, there aren't really too many differences, with the exception of triacylglycerols stored in the adipose tissue, so in fat tissue. So they have about the same amount of circulating fuels available. So this includes things like glucose in your bloodstream, fatty acids and triacylglycerols that are in your system, traveling around from tissue to tissue, okay? And we see that weight-wise, that's not too much. We are dealing with something like 20 grams or so, okay? Glycogen here is given as about 200 grams total. That's probably underestimating the amount that is available. There are about maybe 100, 120 grams or so available in your liver, usually maybe up to 200 grams. And then there is more available in skeletal muscle, up to 400 grams or something like this. So this may be an average here, I'm not quite sure. Proteins, muscle proteins in particular, there's a slight difference here. So a normal man has 6 kilograms available. The obese man has a little more. My guess always is that this heavier man has to support the greater body weight, and maybe has some more muscles that he could actually expend for energy production. What you have to understand though, is that proteins, muscle proteins, are usually only used for energy production as a last resort. Okay, so first you utilize glycogen, and then you switch to lipid degradation. I mean, you also utilize amino acids, and I guess proteins and the amino acids from those proteins that are needed, but muscle protein really is a last resort, and everything else is pretty much depleted. But then if we look at the triacylglycerols available, we see that the normal man, and 70 kilograms is not a lot. Okay, so this is I would say a rather, if it's an adult, a rather slim man actually, still has 15 kilograms of fat that could be utilized for energy production. The obese man, however, has 80 kilograms, which is a lot. Okay. Now, if we consider the approximate density of fat, do you remember what that is? The density of fat. I think I gave you some numbers when we talk about lipoproteins, I gave you some numbers. Compare the density of proteins with the density of fats, lipids, because the differences in density are actually decisive for the composition of particular lipoproteins, decisive for their classification of them. So what do you think that lipids would affect usually? So what happens if you have oil, lipids, and water?
It flows.
It flows. Why does it flow? So what can we tell about the density already?
It's less dense, or low density,
Compared to what?
compared to water.
What's the density of water? 1. So it has to be less than 1, right? Okay, so let's assume that the density of fat is less than 1, okay, in the range of maybe 0.9 grams per cubic centimeter, okay? That's an approximation. So if we think that this obese man has 80 kilograms of expandable body fat, how many liters would that be, approximately? Come on, wake up. If we had a density of 1, how many liters would be 80 kilograms? Do you know that? That's metric system, right? Come on. What does 1 liter of water weigh? Has a density of 1. 1 kilogram. No idea? 1 kilogram. Okay, 1 liter weighs about 1 kilogram. Do you know what one liter is? How much 1 liter is? Bottle of water, okay? So if you think in this volume, we are talking about maybe 90 liters of fat. Okay. So that's a lot of fat actually. It takes up a lot of volume. But that's not really the point here of this table. The point is to see how long these fuels would actually last if these two individuals were to stop eating, okay, and would starve. And would consume energy in the range of about 1,800 kilocalories per day. And to put this in perspective, typically one assumes that if you take up 2,000 kilocalories or something in this range, 1,800, 2,000 kilocalories per day, or large calories, and you just perform your usual activities during the day, that you would not lose nor gain weight. Okay, so that's the amount that you usually just have to expend during a normal day. So if these individuals would just go about their regular activities and would consume about 1,800 kilocalories per day, but would stop eating now, okay, would just take up water and maybe minerals they need, how long do you think that the normal man would actually survive? Just give me a number. Don't do any calculations, just think, how long would you, as a normal man, if they told you 70 kilograms is relatively slow.
100 days or so. 100 days or so.
100 days, you say 3 months or so? That's actually a pretty good guess, okay? Because it's about 3 months. Okay. So often enough, students actually underestimate estimate this tremendously and say something like, okay, a week. Yeah, well, why not? Okay. So how long would you actually survive if you didn't drink anything, do you think? That's something that people usually know. What do you think?
3 days.
3 days? And you think water? What are you thinking? How long could you survive without water?
Yeah.
Okay. Yeah, that's about right. So 3 days or so. So it's much more critical that you actually take up water because you have to flush out all the toxins that you produce when you break down biomolecules. Okay. So, however, if you stop eating, you can. I mean, I guess most of us could survive about 3 months or so. How long do you think the obese man could actually survive? Give me a number. 14. Okay, so maybe you've seen that before. 14 months. Okay. So 14 months would put us at about end of May or so, right, of next year. So if the obese man stopped eating, should still be alive, May 2020 or so. You may think that this is completely hypothetical. It isn't. There have been some, how should I put this, some studies on individuals who starved actually to lose weight and didn't take up any food for an extended period of time. I have some papers on that. And then they were checked on a regular basis, and their blood was drawn, and they actually checked the levels of different metabolites in the blood and such, and measured blood pressure and things like this. And I mean, if you want to lose weight, you can do that. I wouldn't really recommend it, but it's certainly okay to not eat for some time or eat significantly less. Okay, and you can lose a lot of weight actually this way also. But I'm not recommending that. But if you're interested, I can share these papers with you. They're a little older. I think these are studies from the 70s or 80s or something like that. But it has been done. Okay. So, as I said, what we are going to spend most of our time on is the synthesis of fatty acids. Fatty acids are found in most of these lipids and are most important building blocks of many of these lipids, in particular triglycerols and most membrane lipids. So fatty acid biosynthesis occurs primarily in the liver. Okay, so here you see again the importance of the liver, but also in lactating mammary glands, and to a lesser extent also in adipose tissue. And if you remember our discussion of carbohydrate biosynthesis, I made a point out of saying that gluconeogenesis cannot be the mere reversal of glycolysis. Okay, so these are opposing pathways, and they have to be regulated so that we don't usually have both of these opposing pathways occur at the same time. And the same is true also for fatty acid degradation compared to fatty acid biosynthesis. These are opposing pathways, and we have to have the means to regulate these so that they don't occur at the same time to avoid futile cycle. So this slide here shows a rough comparison of breakdown of fatty acids in mitochondrial beta oxidation and biosynthesis of fatty acids. And we see, first of all, there is spatial segregation in cells between the synthesis of fatty acids that occurs in the cytoplasm, as I told you, that occurs in the mitochondrial matrix, as I said before, and the biosynthesis which occurs in the cytoplasm. Okay, and we'll see that this spatial segregation, I mentioned this before, is of great importance also for regulating these pathways and for avoiding that they occur at the same time. Now, if you remember beta oxidation, I hope you do, we saw that it occurs in a couple of steps where we first introduce a double bond in our activated fatty acid, and we saw that FADH2 is produced in this redox reaction. So FAD is actually the electron acceptor, and we also heard then that this FADH2 can be utilized in electron transport and oxidative phosphorylation for ATP. Then we saw that we utilize this double bond to introduce a hydroxyl group, one carbon and a proton on the other. So we actually hydrate this double bond to introduce a hydroxyl group, which then can be oxidized utilizing NAD+ as a cofactor to a ketone. And then we saw that thiolase actually cleaves off a 2-carbon unit in the form of acetyl-CoA. So this is mitochondrial beta oxidation in a nutshell. So if we compare this chemistry that occurs in beta oxidation with the chemistry that occurs in lipid biosynthesis, or fatty acid biosynthesis, I should say, it's not very different, okay? Because what we actually do is that we add 2 carbon units to a growing chain of a fatty acid, and then we pretty much reverse the chemistry of beta oxidation, meaning we oxidize, or we have 2 steps that are analogous to the redox reactions that we have in beta oxidation, and we also have a step where we remove a water molecule. So from that point of view, from a chemical point of view, these opposing pathways are almost the reversal of each other. But there are a couple of significant differences, namely, first of all, if we start here at the bottom of this right side of the slide, where we start with our fatty acid growth or synthesis, we see that the 2-carbon unit that is added to a growing chain actually comes in as a 3-carbon molecule. Okay, this 3-carbon molecule, as we'll see in a moment, is malonyl-CoA, and then we kick out of this 3-carbon dicarboxylic acid a carboxyl group and just attach a 2-carbon unit. Okay, so the growth of a fatty acid also occurs adding 2 carbons at a time, but the molecule that is brought in to add these 2 carbons is a 3-carbon compound, while in our beta oxidation we cleaved off a 2-carbon unit. Okay. Then we have a keto group here in our fatty acid that will be reduced to a hydroxyl group. Okay, so this is a reversal from a chemical point of view of the relevant step in beta oxidation. But the cofactor that is utilized is not NADH, but it's NADPH. And here we see a relatively common theme in anabolism, namely that for most of these redox reactions, we utilize NADPH and not NADH. Okay, so this is a general rule of thumb. I told you that before, that in anabolism, we usually utilize NADPH, but in catabolism, we usually produce NADH, or then also FADH2 often enough, okay? So at this point, we have a hydroxyl group, and we have to remove water. So there's a dehydratase that removes water to introduce a double bond. Interestingly enough, the stereochemistry of this hydroxyl-containing intermediate is different compared to the one that is produced in mitochondrial beta oxidation. So it was the L enantiomer in the beta oxidation. Here it's the dihydroxyl compound in the biosynthesis of fatty acids. And then for the reduction of the double bond, again, the cofactor that is utilized by the appropriate oxidoreductase is NADPH. Okay, so we utilize 2 molecules of NADPH for these 2 redox reactions that we have to perform. And then there's one more difference that is of importance. So we utilized coenzyme A to carry acyl groups in beta oxidation, and in fatty acid synthesis it's a little different. We also bring in our 3-carbon compound, of which we use the 2-carbon compound in the form of a coenzyme A conjugate. But then we'll see that the enzyme that actually carries out fatty acid synthesis, fatty acid synthase, utilizes only a part of the structure that we find in coenzyme A. It has a so-called ACP, which is an acyl carrier protein, to transfer intermediates in our fatty acid synthesis from one enzyme activity to another. And we'll see how that works in a moment. Okay, but first we have to discuss how this 3-carbon compound that is utilized for the synthesis of fatty acids, malonyl-CoA, is synthesized. So this is done by an enzyme that is called acetyl-CoA carboxylase, appropriately marked because it catalyzes the carboxylation of acetyl-CoA. So the acetyl group is coming from an acetic acid that is activated by linking it via thioester bond to coenzyme A. Okay, so we have a 2-carbon unit, and we add to this 2-carbon acetyl group another carbon, utilizing carbon dioxide, bicarbonate, you can say, and producing a derivative of a 3-carbon dicarboxylic acid. Remember, 3-carbon dicarboxylic acid is malonic acid, right? Oxalic, malonic, and so on, succinic. So here we have malonic acid linked via thioester to coenzyme A, and therefore we call it malonyl-CoA. So this is a classical carboxylase reaction, which requires biotin as a cofactor. We talked about biotin containing carboxylases previously, and we talked about pyruvate carboxylase, and we learned that usually these carboxylases require ATP. If we compare the enzymes that we find in bacteria like E. coli, in mammals, overall with regard to the activities that are catalyzed by this enzyme, there aren't any differences. We have 3 components that are of importance. The only difference really is that, besides maybe structural differences, that we have 3 separate subunits in bacteria like E. coli, while we have 1 protein with 3 activities in mammals. And these 3 activities are first a portion of the protein that we can call biotin carrier arm, because there we have, via a covalent amide bond, our biotin cofactor linked to. Okay, so hopefully you remember the structure of biotin here. We have an amide bond here to lysine residue in the protein. Then we have an activity that actually biotinylates our urido, or carboxylates, excuse me, our biotin urido group here to introduce this carboxyl group here. And then we have an activity that is called a transcarboxylase, because it transfers the carboxyl group from our biotin cofactor to our acceptor molecule acetyl-CoA to produce this malonyl-CoA. In this slide, we see that the biotin carrier protein has a more central position and can actually swing our biotin cofactor from one activity, the carboxylase activity, over to the transcarboxylase activity, where then this carboxylation of acetyl-CoA occurs. Okay, so the regulation of acetyl-CoA carboxylase is relatively complex. Okay, it's not 100% understood, I would say. But there have been some interesting observations made. Namely, first of all, that the enzyme is subject to regulation based on phosphorylation and dephosphorylation. The phosphorylation actually is catalyzed by protein kinase A, or CAMP dependent protein kinase, and this phosphorylation actually inhibits the enzyme, and when this phosphate is then cleaved off, we have an activation. I'll show you what happens there in a moment, because it's actually more complex. Then we also have a regulation at the transcriptional level, where insulin actually upregulate production of the enzyme. Okay, makes some sense. Okay, if we have a lot of energy, we can also produce fatty acids. We don't necessarily have to break them down for energy production. And then we also seem to have an allosteric activation by citrate. Now, remember, and this was also a question on the exam, that citrate is kind of a hidden form of acetyl-CoA. It can be utilized for synthesis of fatty acids. So citrate is produced in the mitochondrial matrix, in the citric acid cycle, and can be transported across the inner mitochondrial membrane. We'll see that again in the schematic in a moment. And then can be converted in the cytosol by citrate lyase into acetyl-CoA and oxalic acid. And this acetyl-CoA can then be utilized for fatty acid synthesis, so it makes sense that higher concentrations of citrate would actually activate the enzyme that then is supposed to synthesize or participate in the synthesis of fatty acids by producing malonyl-CoA. Now let's come to this phosphorylation, dephosphorylation again. So phosphorylation actually inactivates the enzyme, while dephosphorylation activates the enzyme. And it has been found a long time ago that the enzyme can actually form polymers. Okay, so there is an individual state where the protein is in a so-called protomeric form. So typically we would refer to this as a kind of monomeric form, so it's just one active enzyme molecule. But then, and that's the case when it's phosphorylated, but then when it's phosphorylated, it actually forms larger polymers and forms filaments that can be visualized on an electron microscope with a quite large molecular weight of about 4 to 8 millions or so. And interestingly enough, this was believed for a long time to be the active state. Now it was then also found that this polymerization actually seems to be induced by high concentrations of citrate. So I think at the current time it's not 100% clear whether it's actually the citrate that activates it and then this polymerization follows, or whether this polymerization is really important. And then there seems to be a 22 kilodalton protein, I think it's called BIC12 or something like this, that also induces this polymerization. But just remember, okay, there are a couple of factors that can regulate the activity of this protein, this enzyme, and then we can also have this polymerization, which is quite interesting. Okay, so we've produced malonyl-CoA now with the help of acetyl-CoA carboxylase, and this malonyl-CoA can be utilized by relatively large protein complex fatty acid synthase in the cytoplasm to synthesize fatty acids. And this occurs in a number of steps where 2 carbon units are added, and then let's say if we want to synthesize palmitic acid, which is actually the primary product of fatty acid biosynthesis, we would have to fuse 8 2 carbon units. Okay, so the first unit would actually come in the form of acetyl-CoA, and then we would bring in 7 molecules of malonyl-CoA to add 2 carbon units of those and kick out 7 carbon dioxides. Okay, so this is just a very brief summary of what would happen in fatty acid biosynthesis. This slide here shows you the synthesis on one slide. I'm not going to go through each and every step at this point using this slide because it would just be redundant to what I do in a moment. but I'm keeping this slide so that you can actually use this as a reference when you try to understand what's going on here. And we'll see this slide again a little later, because I want to point out one thing that is shown in this slide, but not necessarily on the other slides I'm using. Okay, so we have to catalyze pretty much the steps that would be corresponding to a reversal of fatty acid degradation in mitochondrial beta oxidation. Okay, I hope you understand this. So for that reason, we need enzymatic activities that allow us to perform two redox reactions, right? And if we look at the protein components of fatty acid synthase, there are 7 protein components per subunit, and we're dealing with a dimeric protein. We see that there are, where are they? There are 2 reductases. Okay, so there are 2 oxidoreductases which can catalyze the steps that I discussed previously, which in a way can be envisioned as being reversals of the corresponding beta oxidation steps. Then remember, we had hydratase in mitochondrial beta oxidation, so we shouldn't be surprised to find a dehydratase also here in this protein complex. And then we have to have an enzyme that actually catalyzes, where is it? Catalyzes the fusion. We'll see which one it is. This is, I think this one. No, where is it? This one here, beta-keto acyl ACP synthase, that is catalyzing pretty much the fusion of our 2 carbon units, where in the beta oxidation we would have had thiolase to cleave off a 2 carbon unit. And then we see that we have 2 more activities. One is called the malonyl-CoA ACP transferase, the other is called acetyl-CoA ACP transacetylase. And we'll see that these 2 protein components, these 2 enzymatic activities, are important to load fatty acid synthase with the building blocks that we need to produce a fatty acid. Okay. We also see that shown here in a somewhat central position, we have an ACP, acyl carrier protein. So here we will bind building blocks via thioester bonds to a structure that is quite similar to coenzyme A, and then we have one of the protein subunits carrying a cysteine with a sulfhydryl group, to which we can also bind acyl groups via thioester bonds. Okay, so that's just a quick overview of these different enzymatic activities and protein components respectively that we have in fatty acid synthase. So overall, we have 2 monomers of about 270 kilodaltons or so that come together to form functional unit, functional protein, dimeric protein, and we will see that these 2 subunits actually work with each other. Okay, so it's not an isolated subunit that would perform all the steps that are necessary to synthesize a fatty acid, and then the other does the same thing on the other side or so, but these actually exchange intermediates and work together, and that has been known for quite some time. The structure is not 100% understood, and it's also not 100% understood how these 2 subunits or these 2 monomers actually work together in the functional dimer. So let's go through the individual steps that have to be performed to synthesize a molecule of palmitic acid. So in the first step, we actually load this subunit, which is abbreviated KS here, which stands for beta-keto-acyl ACP synthase, with an acetyl group that comes in the form of an acetyl-CoA. So an acetyl-CoA provides an acetyl group that is utilized by this transacetylase to load this sulfhydryl group that comes from a cysteine residue in this KS subunit. Okay, so we just charge this part of the protein with an acyl group. Then a malonyl-CoA that stems from the activity of acetyl-CoA carboxylase, as we just discussed it, is utilized to charge this ACP, this acyl carrier protein part here of our fatty acid synthase, and attach a malonyl residue to a sulfur, which actually comes from a cysteamine, or beta-mercaptoadenine, that is part of a so-called phosphopentythene group that is covalently linked to a serine residue, a serine amino acid residue in the acyl carrier protein, which is part of fatty acid synthase. Okay. And if you look at the structure of this phosphopentythene group here, it's identical with the structure that we've seen in coenzyme A. In coenzyme A, we have this phosphopentythene group, which also carries at the terminus here the cysteamine group, to which we can link acyl groups. But then this phosphopentythene group is linked to this structure, which is an adenosine 3-phosphate, and we have another phosphate here at the 5' carbon. So this is coenzyme A, okay? And the structure shown in red here is what we also find as a prothetic group in this acyl carrier protein. So it's just, you could look at it as an analog or a derivative of coenzyme A, okay? And just as we could via thioester bonds link acyl groups, fatty acids, okay, to this sulfhydryl group in cysteamine in coenzyme A, we can link acyl groups to this sulfur here in the cysteamine in our phosphopentythene group that is part of the acyl carrier protein. Okay? So, this structure here is now covalently linked to a malonyl group, which was brought in as malonyl-CoA, which resulted from the synthesis of malonyl-CoA catalyzed by acetyl-CoA carboxylase. And at this point, we have a acetyl group here on Ks and a malonyl group here at the acyl carrier protein. Now, what this beta-keto acyl ACP synthase then catalyzes is a transfer of this acetyl group linked to Ks, which is conveniently shown in yellow here, to our second carbon here in the malonyl component. Okay, so we have condensation reactions called here, transfer of this 2-carbon unit to this 2-carbon unit shown in red here. And the chemistry behind this is actually that this carboxyl group that was previously introduced to our 2-carbon unit in the malonyl, in the acetyl-CoA carboxylase reaction, is kicked out to produce a better nucleophile. This nucleophile, a carb-anion, attacks this partially positive carbon here in our thioester, okay? And we have a covalent bond between this carbon and that carbon, and we kick out carbon dioxide, okay? So what this produces is a 4-carbon keto acid, which actually is nothing but a beta-keto butyric acid now linked to the acyl carrier protein. So this is the very same structure that would have resulted from the degradation of an even-numbered fatty acid up to chain lengths of 4 carbons, and then thiolase would have come in, attack here, and cleave off acetyl-CoA. Okay, but now we're talking about the biosynthesis of fatty acids, and this is our first, so to say, intermediate that we produce. What I want you to understand here is that the formation of this covalent bond here to link the 2-carbon unit here to this 2-carbon unit, shown in red, doesn't consume or does not directly consume ATP, does not directly consume energy, which could be surprising. However, it does consume energy because, indirectly, because we had to invest energy for the carboxylation of acetyl-CoA to produce malonyl-CoA. So the whole idea behind, the whole rationale behind this acetyl-CoA carboxylase reaction really is to produce a structure which is active enough that we can have this formation or this transfer of a 2-carbon unit to this carbon here. So we activated this carbon here by introducing a carboxyl group. So indirectly, we consume energy by producing this malonyl-CoA, but then for the formation of the covalent bond here in the fatty acid synthase reaction, we don't. Understood? Okay. And this kind of decarboxylation to produce a reactive nucleophile in the form of carb anion is something that we are going to see again probably next week. We'll continue talking about lipid biosynthesis. Okay, so what do we have to do with this keto acid now? Think reversal of beta oxidation. We have to reduce it to hydroxyl. Okay, why not do that? We utilize not only appropriate oxidoreductase, which is called beta-ketoacyl ACP reductase. It's part of the fatty acid synthase. We utilize NADPH as a cofactor, as I said before. We reduce the ketone here to a hydroxyl group. I talked about the stereochemistry of the resulting hydroxyl compound. It's a D enantiomer. What do we have to do next?
Lose water.
What's that?
Lose water.
We remove water, so we have a dehydration. Okay, why not use a dehydratase for this beta-hydroxy acyl ACP dehydratase? We remove a hydroxide ion from this carbon, a proton from this carbon, which is water. We introduce a double bond. Okay, it's a trans delta 2 double bond. What do we have to do next? Reduce it. Okay, reduce the double bond, utilizing NADPH and appropriate reductase, ACP reductase, to form a saturated fatty acid. It's short here, it only has 4 carbons at this point. Butyric acid still linked to our acyl carrier protein. Okay? So, if we want to extend the chain length now, we actually transfer this intermediate, which is at this point is butyric acid, to our KS subunit again, the beta-ketoacyl ACP synthase reaction. That's done with the help of this transacetylase. And then we have to bring in another malonyl-CoA, charge the acyl carrier protein again with a 3-carbon dicarboxylic acid, malonic acid, and then again have a nucleophilic attack here of the second carbon into this thioester carbon, partially positive. We kick out carbon dioxide, produce the corresponding beta-keto acid, which then we are going to reduce again to hydroxyl, dehydrate, to introduce a double bond, reduce the double bond, and have a 6-carbon long fatty acid. Okay, so hexanoic acid, pretty much linked to ACP, and then we transfer it again over here, bring in another malonyl-CoA or malonyl residue from malonyl-CoA, and extend it again by 2 carbons. So we have to go through this reaction actually 7 times to fuse 8 2-carbon units to produce the major product of fatty acid synthase, which is palmitoyl ACP. Okay, so palmitic acid, 16 carbons, no double bonds, linked to the acyl carrier protein. Understood? So, before we take a look at the overall reaction, let's talk quickly about how these 2 subunits in our homodimeric enzyme work with each other. So for the longest time, it was believed that the two monomers actually associate in a so-called head-to-tail conformation, meaning that if the carboxy terminus of one subunit is on one side and the amino terminus on the other side, that the orientation would be different in the other subunit. Okay? And then it was already known that these two subunits would actually share activities. And this is shown by these arrows, where we have our intermediates, the different lengths, fatty acid residues linked to ACP here, moved around between different activities from one and from the other subunit. Okay. Now, somewhat newer studies actually questioned this model and said, okay, there's a different conformation that is assumed by the two subunits, and someone in 2005 came up with a nonlinear coiled conformation. Here the abbreviations here are a little bit different compared to what we saw previously, so I added the names here. But I think the bottom line and the major take-home information is that it's still believed that these two subunits share activities. Okay, so let's take a look at the overall reaction, the stoichiometry of the synthesis of palmitic acid. So again, palmitic acid is a major product of the synthesis of fatty acid synthase. We need 8 2-carbon units. Here it's shown as 8 acetyl-CoA molecules. Now, that may be considered an oversimplification. That's just the net reaction here. What we really need are 1 acetyl-CoA and 7 malonyl-CoAs. And the 7 malonyl-CoAs are produced from 7 acetyl-CoAs, and carboxylation of those, which requires 7 ATPs. Okay? So that's why we have these 7 ATPs here. And of course, we also would need some carbon dioxide or bicarbonate to do this reaction. Then we saw that we have, for each addition of a 2-carbon unit, we have 2 redox reactions. Both of these require NADH. So if we go through this reaction scheme 7 times, 7 times 2 is 14 NADPH molecules that are required, okay, to produce a palmitic acid that at this point would still be linked to the acyl carrier protein. Okay. Now we also have seen that we have 1 dehydratase reaction for each cycle. So if we go through the cycle 7 times, we should actually produce 7 molecules of water, and we do that. Okay. However, what is shown here for the overall reaction, the stoichiometry of palmitate synthesis are only 6. And the reason for that is that you actually utilize a water molecule to cleave the thioester bond between our palmitic acid, palmitate, iodized, and the acyl carrier protein. Okay, so from a stoichiometric point of view, you do produce 7 molecules of water in the 7 dehydratase step, but then 1 molecule of water is utilized to hydrate, not the very same that is produced, okay, but from a stoichiometric point of view, you use 1 to hydrolyze the bond to produce palmitic acid. Okay? So, this overview just shows us again where the acetyl-CoA for fatty acid synthesis comes from. It comes from citrate that in the cytoplasm is cleaved by citrate lyase to oxaloacetate and acetyl-CoA. So the acetyl-CoA that really is transported here in the form of citrate across the inner mitochondrial membrane is produced in the mitochondrial matrix. And the sources here are glucose, it's converted to pyruvate, as we know, and pyruvate dehydrogenase in the mitochondrial matrix then produces acetyl-CoA, and then there are also ketogenic amino acids that produce pyruvate, produce acetyl-CoA, and this acetyl-CoA can also be transported across the inner mitochondrial membrane in the form of citrate. Okay, so we talked about the necessity of also having transport system then to allow pretty much indirect transport of oxaloacetate back across the inner mitochondrial membrane. There is no oxaloacetate transporter, but we learned previously in the context of the malate aspartate shuttle that we can easily convert oxaloacetate into malate utilizing cytosolic malate dehydrogenase. Malate can then be transported back into the mitochondrial matrix and then be converted back to oxaloacetate. We talked about this before. We see a somewhat different route here also for our malate. At the bottom of this slide, we chose that in the cytoplasm we can also convert malate, the decarboxylation reaction, to pyruvate with malate enzyme. Pyruvate can be transported across the inner mitochondrial membrane by a pyruvate transporter, pyruvate translocase, and then can be carboxylated with the help of pyruvate carboxylase to oxaloacetate. Now, what is important about this reaction, I mentioned this when we talked about anaplerotic reactions or the amphibolic nature of the citric acid cycle, is that this reaction is one of the few reactions that actually produces NADPH. Okay, so NADPH is very important for biosynthetic reactions, as we've seen here in our discussion of fatty acid synthesis. However, there are only a few reactions and pathways that produce NADPH. Pentose phosphate pathway is one pathway, and there are reactions that produce NADPH. Malate enzyme produces NADPH. We heard about isocitrate dehydrogenase in the citric acid cycle. And I told you that there's also cytosolic isozyme that can actually produce NADPH. So since there aren't too many reactions that produce NADPH, this is actually quite important reaction. The ratio of NADPH to NADP plus in the cytosol is somewhere in the range of 75 to 1 or so. So there is an excess of the reduced form of this cofactor of NADPH, which is largely responsible for the reducing environment that we find in the cytoplasm. So you may know that in the cytoplasm we have a reducing environment, okay? And since we have higher concentrations of NADPH there, we maintain this reducing environment. It's quite different actually for NADH. So NADH to NAD plus is actually quite different than for each molecule of NADH that we find there in cytosol. We have about 1,200 or so molecules of NAD plus. Okay, so the concentrations of reduced NADH actually in the cytoplasm are quite low, kept quite low, but NADPH is actually much more abundant, quite a bit more abundant than NADP plus. So let's take a look at the regulation of fatty acid biosynthesis overall. We talked about and touched upon the regulation of acetyl-CoA carboxylase, which we see here in the center of the slide. Talked about a couple of things. So I said that the phosphorylation, which triggers an inactivation of the enzyme, can be a result of glucagon or epinephrine binding to appropriate receptors, and then we have the signal transduction cascade that we talked about previously in this class, which activates protein kinase A, and protein kinase A can also phosphorylate acetyl-CoA carboxylase, and then we have an inactivation. Okay, and we've also talked about some activating activity of citrate. What is interesting is that palmitoyl-CoA also seems to deactivate or reduce activity of acetyl-CoA carboxylase. Now, with regard to citrate lyase, which we need to cleave citrate to acetyl-CoA and oxaloacetate, it's actually activated by insulin. And then I have added actually something here that shows the role of malonyl-CoA, because if we look at the fatty acid biosynthesis not as an isolated pathway, but compare it with fatty acid degradation, malonyl-CoA plays an important role to make sure that we don't have these two pathways occur at the same time. And I think I mentioned this briefly before when we talked about degradation of fatty acids. The transport of fatty acids across the inner mitochondrial membrane from the cytoplasm into the mitochondrial matrix is actually inhibited by malonyl-CoA, which is pretty much the first molecule in the synthesis of fatty acids, because it inhibits this carnitine acyl transferase 1, which we needed in this process of transferring fatty acid CoA conjugates across the inner mitochondrial membrane. So when our cells realize that it's not the time to break down fatty acids, but to synthesize fatty acids, and we produce malonyl-CoA, then malonyl-CoA will also inhibit the transport of fatty acids across the inner mitochondrial membrane so that they can't be broken down by mitochondrial beta oxidation. And then I also added that we also have a long-term regulation via insulin-activated stimulation of synthesis of acetyl-CoA carboxylase and also fatty acid synthesis. Okay, so at this point, I'm asking you to turn off all the recording devices and computers and put them away.